Buenos días a todos. Mi nombre es Agustín Breña, soy coordinador de hidrología del Instituto Mexicano de Tecnología del Agua. El día de hoy tenemos el gusto de tener, nuestro primer ponente internacional, que es el doctor Luca Brocca, de Italia. Él nos va a hablar. Él es el primer ponente de una serie de conferencias que impartiremos esta semana sobre percepción remota e hidrología. Y bueno, el título de su plática de hoy tiene que ver con la humedad del suelo, una variable clave para predicciones hidrológicas, tanto para inundaciones como para aludes y también para sequías. Ahorita voy a dar una breve reseña, la voy a dar en inglés, ya que el seminario va a ser en inglés. Del doctor Brocca antes de empezar. La doy en español, la puedo traducir fácilmente. Bueno, el doctor Luca Brocca recibió tanto su maestría como su doctorado en ingeniería civil en el 2003 y el 2008 respectivamente. Desde el 2009 él es investigador en el Consejo Nacional de la Investigación en Italia, en el Instituto de Investigación para Protección Geohidrológica en Perugia, al centro de Italia, y desde 2019 es el director de investigación. Ya en sí, como investigador, es autor y coautor de más de 140 artículos indizados, de los cuales en los últimos 5 años ha publicado 74. Tiene más de 70 artículos en conferencias o en capítulos de libros, y pues es un autor bastante prolífico. Él al día de hoy tiene más de casi 8,000 citas académicas, con un índice H de 45. Y bueno, además de ser pues un científico, un investigador con mucha capacidad de generación de todo este conocimiento. También él es un partidario de los datos libres, y él ha publicado hasta la fecha más de 10 bases de datos globales sobre humedad del suelo y precipitación, y 8 modelos hidrológicos. Él ha impartido más de 50 presentaciones en conferencias y seminarios, 22 como invitado, como ponente magistral, y también ha organizado varias conferencias internacionales. Él también es revisor en más de 50 journals, más de 50 revistas indizadas, y también organizaciones o consejos, organizaciones científicas a nivel mundial. Y él ha sido o es parte se encuentra en el comité editorial de varias revistas, como es el Journal of Hydrology, Scientific Reports de Science, Geoderma, Frontiers in Water, Hydrology y Remote Sensing de MDPI. Él también ha sido y es investigador principal en varios proyectos de investigación, tanto italianos como europeos, y también varios de ellos han sido financiados por agencias espaciales internacionales, principalmente la ESA, que es la Agencia Espacial Europea, la EUMETSAT, que es la Organización Europea para la Explotación de Satélites Meteorológicos, y también para la NASA. Entre varios de sus logros, pues en el 2012 recibió la distinción de Early Career Research Excellence, otorgada por la sociedad IEMS, y en el 2018 fue el ganador de la competencia Copernicus Masters en agricultura inteligente, y en el año pasado fue nominado por el Web of Science Group como un investigador altamente.
So thank you very much for your introduction in Spanish, or I don't know actually if it is Spanish or other language, but thanks for the invitation. I'm happy to give you this online seminar on Saint Mostod. I will give a talk, actually, yeah, of course, related to Saint Mostod as a key variable for hydrological prediction. And I will speak you about this variable, how it can be used for floods and slides, drought, and also precipitation. I would like to thank all my colleagues in our lab that, who of course is collaborating with me for the job we have done and for most of the things that I'm going to present you. Let's start from the beginning. So what is a Saint Mostod? Most you background again.
Okay.
I will continue. Yeah, but
then get away, city.
Okay, thanks. So let's start from what is Saint Mostod. Saint Mostod is a key variable in the climate system, and the definition of Saint Mostod is the amount of water stored in the unsaturated soil zone. And actually it is estimated as the volume of water in the pore of the unsaturated zone. But its definition is easy in principle, but different disciplines gives a different meaning of the same terms. And so Saint Mostod can be seen in absolute terms from or in as a ratio of saturation. So it is between 0 and 1. So basically it means that 0 is totally dry and 1 is totally wet. And also in volumetric water content. And so we have different definition of Saint Mostod. So throughout this presentation, I will mainly refer to Saint Mostod as a saturation content, so between 0 and 100%. Also because we believe that the main and the most important Saint Mostod is much more important to be considered as a dynamic variable. And so the temporal dynamic of Saint Mostod is much more relevant than its absolute value. I will not provide you, of course, details on what I'm saying to you because it's difficult in a presentation and also, for instance, in this webinar. But you can find on the right side of each slide some reference. You can go to the reference and having all the details on what I'm saying. So I'm working with Saint Mostod basically from the beginning of my research career at CNR in Italy. And we have started from the monitoring of Saint Mostod at the local scale with in situ measurements at a very local scale for instance, one field or a small catchment. Then we started looking at satellite data and we started investigating how much Saint Mostod vary in space and in time, because it is very important to understand how can we monitor Saint Mostod at different scales. And if we have, I don't know, satellite data or in situ observation for monitoring Saint Mostod, how many measurements we should take, or this kind of question should be answered. Starting from that, we started to understand that Saint Mostod can be used also from, for instance, few in situ stations you can use for doing hydrological prediction. And so the first application, basically we are hydrologists, and so our main application is related to the floods. And so our first application was the assimilation of Saint Mostod into hydrological modeling, but much more details on this kind of application will be given by my colleagues on next Wednesday at the same time. And then we started to make what we say doing hydrology backwards. So actually we see Saint Mostod not as an indicator of rainfall. The classical definition is using Saint Mostod as using the soil as a natural rain gauge. And so we developed this kind of algorithm called SEM to rain that basically from inverting Saint Mostod data we get precipitation. And recently, also because people started saying us that over-irrigated field, we are doing something bad, because over-irrigation, we don't see only precipitation, but we see precipitation plus irrigation. But it's good because actually we can estimate from soil moisture also irrigation. And so we started these activities in 2018. And these two activities are the main activities that on which I'm working in the last couple of years. I will give you more details later. So why soil moisture is important? Here, just a couple of examples. In the top, you see the example for the water balance, for the mass balance. You can see two pictures of one basin, on the bottom, a dry basin, and on the top, a wet basin. And you can easily see that after the same amount of precipitation, for instance, the response of the basin in terms of flood is much different. And it is due to soil moisture. But soil moisture also governs the partitioning not only of the mass, but also of the energy fluxes between the land surface and the atmosphere. And so it's important for a number of activities. And this is probably why I was lucky in my research activities, because actually we work not only with floods, but also for drought, for weather prediction, climate system, landslide, crop production, and you can also say something else. I will give you some details on some of the main activities on which we are working, but of course, most can be used also for other applications. How can we monitor soil moisture? We have basically, as most of variables, we have 3 different techniques. In situ techniques that provides you very accurate measurements, but they have the problem of being punctual measurements, and it can be hard to specialize these measurements. Then we have satellites that basically I did this slide probably 10 years ago. Now satellites data are much more accurate, and also the spatial resolution has been increased a lot. So 10 years ago, I'm saying that the resolution of satellite is too coarse for monitoring soil moisture, but probably now this is not anymore the case. And finally, we have modeling. So for instance, we started, as I told you at the beginning, monitoring soil moisture in a field, and you can see in the top left, but also in the laboratory. And we can have estimators of soil moisture like a maps in the bottom left, or like a time series of soil moisture at different depths. We started analyzing this data to understand what is the variability of the data, if there are some pattern or something that can be reconstructed from this data to use this data for catchment scale applications. Currently, we have this international soil moisture network that is hosted by 2VN, and this network basically hosts, I don't know exactly the number of stations, but you can see that there are a lot, even though they are not equally spaced over the globe. But all these data are freely available, and so you can download them. And so if you want to make some analysis with soil moisture data, with in situ soil moisture data, you can download such data. And also this archive is dynamic in time. So probably if you go now in the website, you can see a larger number of stations. Closing with the monitoring soil moisture, I close with this slide, just one slide that basically summarizes, let's say, 4 or 5 papers that we have been done for the monitoring soil moisture. But it's important for this webinar to let you understand that the picture on the left shows you the time series. The black line is the mean soil moisture for a catchment with more than 200 measurements. And what we have started to understand, if we have only 1 measurement or 10 measurements or 5 measurements, how accurate is our estimate of the mean soil moisture? And you can see from the shaded area that basically just with 1 or 5 measurements, you can reconstruct reproduce quite well the mean soil moisture at the catchment scale. So it means that with few measurements, we can estimate soil moisture at catchment scale. This picture comes from a paper, but we have several of them, and we can say that with let's say 3 to 5 measurements, we can have an indicator of soil moisture at catchment scale for catchment, for instance, of 200 square kilometers. And with the same reasoning, we can say that we can use remote sensing data, most of them as a coarse resolution, 20 by 20 kilometer. They can be used for smaller scale application. So this downscaling or upscaling property of SoilMaster is important for the use of the data in application, because typically you, for instance, you say, okay, SoilMaster from satellite is 20 by 20 kilometer. I have my application at field scale or for a basin of 100 square kilometer, it can be used. Then the first message from this presentation and from our job is that actually it is not true. You can try to use the data and probably you can find something useful for you. Now a number of slides with remote sensing of SoilMaster. Probably most of you live close to US, and so you all know the SMAP mission, the SoilMaster Active and Passive Mission. That is the first mission dedicated to SoilMaster from NASA in 2015. And this mission was launched by NASA, and is probably currently is the most accurate measurement of SoilMaster that we have from space. But likely we don't have only SMAP. We have really a huge number of sensors from satellites that can be used for measuring SoilMaster, starting from 1978. That was the year in which I was born. So it's more than 40 years that we have SoilMaster data from space. And we have a number of sensors that can be active and passive sensor, and also a number of products. All these products, most of these products are freely available, so you can download them and you can use. For instance, one of the longest time series is from the product called ESA CCI, which means European Space Agency Climate Change Initiative, and it is a 40 years data set on a global scale, available at 20 by 20 kilometer resolution, but it's a very long term. But currently, we are going also at high temporal and spatial resolution with, for instance, Sentinel-1. Sentinel-1 is the mission from ESA. And you can see here an example in Italy. If you focus on the figure on the right, so in the middle of the slide, you can see precipitation for 10 of July and 11 of July in Italy, so for 2 consecutive days. And on the right, you can see the footprint of precipitation on the land. And you can easily see that there is a very good agreement in space of the footprint of precipitation on SoilMaster, and it is also at high spatial resolution. To have an understanding of how accurate in space can be the new SoilMaster data that we can get from Sentinel-1, here it is an example for an agricultural field in Sardinia. Sardinia is one of the islands in Italy, very nice for going for tourism. But here it's a agricultural area in which each field is around 1 hectare. And you can easily see that with the Sentinel-1 data, you can track SoilMaster for each individual field. And so, for instance, if you work on agricultural application, it's really a very important source of data. Now, how accurate are satellite SoilMaster data? I can't answer in a presentation, but I just provide you a couple of slides. This is just because it was one of my first jobs with satellite data in 2010, in which I do the validation of satellite SoilMaster data for a number of sites in Europe. At that time, we didn't have the international SoilMaster network. So I collected the data by myself, and I do the comparison of different sites. In this slide, you can see on the x-axis the different location, and on the y-axis, you have the correlation between 4 different satellite products and in situ SoilMaster data. You can see that, for instance, correlation is different from different products, of course, but for instance, the red line, that is the ASCAT SoilMaster product, has an average of correlation equal to 0.85. This was done for 18 sites, or probably 18 sites in Europe, but now, and this is an example of time series of SoilMaster. This is very important to me to show you this time series, because the green line is the observation, and the red and blue line is satellite data, with the 2 different post-processing of the data, but basically the results are the same. So you can easily see that satellite data can track almost very good with, for instance, peak and valleys very well reproduced. You can see that after a rainfall event, it almost goes up, and also from satellite it is the same. We have some problem in winter time. Winter time in Italy is, I don't know if you can see my pointer, but winter time is for instance, in January 2008, and you can see that there is a drop because for frozen conditions, almost from satellite can't be estimated. So if you want almost data over the Alps, you have problems. But in any case, if you look at the overall time series, there is quite a nice agreement. After a number of years now, for instance, we have a large number of studies doing the validation of satellite almost data. Now probably we have more than, I don't know the number of papers, but for instance, this paper do the evaluation for close to 2 billion measurements in different sites located everywhere in the world. And here on the right, you can see the plot of the box plot of correlation for different measurements network. And again, the correlation is quite good, higher than 0.7, 0.8 for the good networks. But for instance, if you try to make measurement from satellite over these FMIs is located in Norway. And so it is very frozen and there is no condition. And so in this case, so the correlation is around 0, and similar problem you can find for the SNOWTEL network in the US, in which most of the stations are located at very high altitude. So if you want some master of a frozen or snow condition, it's not good from satellites, but otherwise it can be a good source of data. And now we have some satellite data. As I told you, for instance, if you want satellite data from SMAP or from SMOS, they are freely available and you can download them, but some product is also operationally available. It means that they are available, for instance, with the latency of a few minutes. And so you can use the data in real-time application, or with a latency of, for instance, 1 day. And most of the data are provided by the Copernicus program. Copernicus program is the Copernicus funded by the European Commission, together with in this case, together with the European Space Agency. And they provide the different satellites and master product operationally, and you can use this data. And for instance, you have now the product of master from yesterday. And I will show you some example of using this data for operational application that we are doing in Italy. And of course, like this webinar, we do some, I don't like the term course, but we do some training of, or let's say we share our experience on the use of satellites and master data with people that could be interested to use the data. And so we do international courses also in the framework of the EUMETSAT HSAF project. HSAF is the EUMETSAT project for the satellite application facility for hydrology, and we do courses in this framework. And it is expected that in the coming years, the courses the number of courses will increase, because we see more and more the interest of people in using the data, and some training is of course is needed. But let's start with the application. The first application is this figure shows you why soil moisture is important for floods. The picture on the bottom shows you, the colors are not really good, but the red means very high soil moisture condition. And so basically during this day, it is the first day of December in 2010, we have a very high saturation condition. This is the picture of the basin in central Italy. And so on the right, you can see that we have a flood condition in many stations in the whole region. And so for instance, you can see on the bottom right of these plots that some of the stations also overcome the threshold, and so we have a flooding. One day after, the same day of the year, so which means the 1st of December in 2011, you can see the map on the bottom right, and it is totally blue, which means in this case, totally dry condition. So the same day of the year, we have very different soil moisture conditions. So we say that soil moisture is the same. For instance, in December, soil moisture is wet, and in July, soil moisture is dry in Italy, as we expect. The condition can be very different. For instance, 1 year later, we have very dry condition, and we have, for instance, drought problem in Italy in 2011. 1 year later, again, I was giving a presentation, and actually it's something like today, in which we have heavy rain in Italy, even if we are in June and we don't expect heavy rain. But in any case, in the same day of the year, we have again very wet condition, and we have a flooding. So this means that we need to know, we need to have a measurements of soil moisture over time to understand any kind of measurements that can be from in situ data or from satellite can help us to improve hydrological prediction, as hydrological prediction are very strongly related to the amount of water into the soil and to soil moisture. So that's why, for instance, this is just one of the applications that we did with soil moisture. Much more details in terms of floods will be given by Christian Massari next Wednesday. And so I basically am saying you to attend his seminar. And this simple model that he developed, basically we directly use the soil moisture data and we put in a very simple hydrological model. It means that we are able to run a very simple hydrological model without the need of long-term rainfall or evapotranspiration data that can be a problem to get this data, particularly in unreached areas or in data scarce regions. And the model is very simple, and so it is very good for operational purposes because it runs in a couple of seconds. And we found that we have two papers on this on the application of this model. One is for a project that we run in Greece, in which we apply the model to make flood prediction for a small basin in Greece. And for instance, the plot shows the gray line is the observation, and the black line, the dotted and the dashed lines, are the prediction from two different satellite data. And most of the time we found that this kind of modeling is providing very similar performance with respect to more complex hydrological model, which run, for instance, in a continuous way. And so basically this model can be used for flood prediction with some success. Typically, when you are in condition in which you don't have accurate or long-term data. Second application, the first was floods. The second application was rainfall, and I will provide you just a few details on this algorithm that is called SM2Rain. It was born, let's say, in 2014, 2013. In which basically this approach is a new approach for measuring soil moisture from space. Typically we measure soil moisture, for measuring rainfall from space. Typically we measure rainfall from space looking at the clouds. So it's a typical top-down approach in which we see the clouds, and from this information we get precipitation information. We basically do the opposite. We look at the soil, and from the soil we are able to estimate precipitation. We have a number of applications, but for instance, you can see in the animation on the left that shows on the top the monthly precipitation that we get from SM2Rain, and in the bottom the monthly precipitation that we get from ground data. And you can easily see that the two maps are quite in a very nice agreement. And again, if you want more details, you can find it in the papers. But the most recent data set that is freely available can be downloaded on the link that you see in the bottom of the slides, and provides information of precipitation at every day with a spatial resolution of 12.5 kilometers on a global scale. And it is, in principle, it can be available in real time. We are working towards providing this data set in real time, but we are not at this stage now, but it will be in the near future. And this data set is from 2007 to 2019. But of course, we are not saying that our way of estimating precipitation is the only way that that is possible. And we also are integrating the typical approach that is, for instance, from the mission, from the GPM mission. GPM is the Global Precipitation Measurement Mission. That is the typical way of measuring precipitation from space. And we found that integrating GPM plus our approach, we are able to get even better, much better results. In the bottom right, you can see some maps of Africa in which the colors are saying you how accurate the products are. So if you look at greener is the map, it means that better is the data set. And you can easily see that the GPM plus estimate terrain product is the best among the four, and it's even better than the analysis of the product from ground station. So for instance, our basically message now is that if you want the precipitation data and in Africa and also in Southern America and partly also in Mexico, it's our product seems to provide you very good performance. The map shows you the mean annual precipitation that is very close to our expectation, with a large amount of precipitation over the tropics area, and also with some nice pattern over the Alps or over the mountains. All these products have a spatial resolution of 20 kilometers, but now we have Sentinel-1, as I told you some slides ago. So applying estimate terrain to Sentinel-1, we are in principle able to provide estimates of precipitation at a resolution of 1 kilometer. And this is something that we are working in this year, and in the recent year, we have a paper already published with some first results in Italy, and the animation shows the comparison between on the left, yes, our estimates, and on the right, the observed data. But of course, you can't compare them because we don't have in situ data of precipitation at 1 kilometer scale. And so actually, we should make the comparison, for instance, with radar data, but we don't have this data for this. We didn't use this data for this study, but in principle, now we can estimate precipitation at 1 kilometer scale. And also, I want to underline that, for instance, there are some plans from European Space Agency to launch a geostationary microwave satellite. It means that the same map that, for instance, now you see in the infrared bands, that, for instance, yeah, in Europe we have Meteosat. I don't remember the name of it. Should be GOES, the name of the satellite that you have in US. But these data are available at, for instance, 3 kilometer resolution every 15 minutes. So in the future, we could have this kind of spatial and temporal resolution from the microwave. So it means that we can get thermost and then precipitation at every 15 minutes with a spatial resolution of few kilometers. And so it means that basically we can completely revolutionize the way we are measuring precipitation from space. But this is for the future. And as I told you, we are working for providing real-time precipitation from our approach. This is an example of the cyclone Idai that hit Mozambique in 2019. And you can see the animation that shows basically the cyclone that hit the Mozambique region quite nicely. And this is done through the integration of our approach and the top-down approach, because actually the cyclone started from the sea and we can see rainfall only over the lands. But the integration of the two is providing a very nice product that it will be available. This product available for the Europe and Africa, and also part of Brazil will be available probably by the end of this year in real time. So which means that today you have the precipitation from yesterday. And of course, why we are not basically a developer of satellite product, even though we started after 2 estimate terrain, we started doing this. But our main job is related to hydrology, and so to simulate floods. So we are using precipitation from estimate terrain to simulate floods basically everywhere. And for instance, this study is that is currently under discussion, and you have the link on the right, is for 1,300 basins in Europe, in which we compare 3 different products, in which, for instance, TMPA, CMORPH, and estimated rain is on the right. And the map shows the performance. Higher is the value of KGE, better is the performance, which means that bluer is the maps, so it means that the product is better. And you can easily see that our maps is the map from estimated rain ASCAT is quite blue and better than the others. And so it means that our product is particularly suitable for flood prediction. And this is confirmed not only in Europe, because as I told you, we are good in Africa. And so we started doing the same analysis in Africa. And this is for a number of basins that we have, for which we have collected the data. But for instance, at EGU, and you can see the presentation online, there is the link again, we do the analysis for around 400 basins also in Africa. And you can see, for instance, this is just one basin, but you can, if you want, I can also provide you precipitation data for every basin everywhere. But on the top, you see the precipitation from GPM, and on the bottom from estimated rain ASCAT, and you can easily see that the agreement is quite good with between the red line, that is the simulation, and the green line, that is the observations. And likely we are not the only one using our product for doing flood prediction. This nice study was carried out by some colleagues and they do the flood simulation for 8 basins throughout the world. And they made the analysis with different precipitation products. We should focus only on the green products, which are the products based only on satellite, because of course, if you use products including gauge station, your performance will be better. But if you look at the green box plot, again, higher is the value, better is the performance. You can easily see that, for instance, estimated rain ASCAT is found to be the best one among the other satellite-based products. We can use SunMostu not only for floods, but also for landslides. This is a study that we did. This is just one slide that I want to show you, because basically this is for a small landslide for an area that is, I don't remember exactly, but it's less than 1 hectare. And we have an important landslide because it is close to the streets. And so it is monitored. And from the monitoring of the landslides, we get the green line. The green line is the displacement of the landslide over time. So basically we need to predict these displacements to understand what the movement of the landslide over time. And we did a simple experiment by using, if you use only precipitation and a simple linear regression, what are the results that we get? And we get the red line on the top, that basically it says us that we are not able to predict the movement of landslides. If you use precipitation plus antecedent precipitation index, that is typically index used for as an indicator of SunMostu, performance increase. But if you use also satellite data, and these satellite data are 20 by 20 kilometer resolution, performance increase a lot. And if you use all the data that are available, we are able to get, for instance, correlation equal to 0.88 and quite a nice agreement with observation. So it means that using coarse scale resolution data, we can get SunMostu that is not really the SunMostu for that landslides, but is an indicator of the SunMostu condition of that area that can be used as a proxy for understanding the movement of landslides. And that's why, for instance, in our region that is in central Italy, the center which is in charge of doing landslide prediction is now using a system called Presca, and more details again in the paper. This system is based on a threshold based on rainfall and SunMostu. Typical threshold for doing landslide prediction are only based on rainfall. For instance, intensity, duration threshold. We here implemented the rainfall SunMostu threshold in Umbria region, and at the end we get with on the bottom you can see these semaphoric maps in which day by day, they use such system, and they use indeed semester data for space for getting information of the warning level for landslides occurrence over the region. And what we have been doing also by using SM terrain is extending the analysis for the whole Italian country, because in Italy we have problem with landslides. We have collected, for instance, a list of more than 2,200 rainfall-induced landslides from the geomorphology group of our lab, and we have used this data set to test different satellite precipitation products. And the figure here in the center, and again you can see the paper, is the final message. And this picture is a rock curve. Basically, if the lines are closest to the point on the top left, that is called PCP, closer the lines are to this point, better are the performance. So if you make the analysis with different satellite precipitation product, like blue line, green line, magenta, and red line, closer are to this point, better are the performance. And we found that our product is quite good in reproducing the occurrence of landslides, and it can be used for such a purpose. And that's why we are now working on using a system in which we use satellites and master from space, that you can see on the top left. We can estimate also precipitation, and so from the same system we have soil moisture and precipitation, and so we can do a threshold like system in which day by day we can provide the landslide alert map. But we can also not only providing a map in which we say, for instance, red pixel means critical condition, but we can also say to the people how much rainfall is needed for the occurrence of landslides. So if you have a meteorological prediction for the future, and your prediction told you that is 100 millimeters are expected in the next day, we can say if this amount of rainfall can be critical or not in your region. Finally, we go for drought, and the use of SonMaster for drought application is the easiest way of using satellite SonMaster data, and we started doing this in 2017 because we have, you can see on the right, we have a very strong drought condition in central Italy, and I was asked to people also from journalists how strong is the drought condition, and we started to make this anomaly map of SonMaster from space that is really a very easy computation. And in this plot, for instance, you can see the animation from the beginning of June of 2017 to July. Now we are in July, and red color means dry anomaly condition. And from this map, you can easily see the evolution in time and in space of drought condition. For instance, this slide shows you the time series of SonMaster anomalies for different locations in Europe. Starting from the top, you have Poland, then UK, Germany, France, Spain, and Italy. And the time series goes from 1997 to 2018. So for the last 20 years. And so you can easily see, of course, the time series, if it is blue, it means that SonMaster is higher than average. If it is red, the opposite. And so, for instance, you can easily see that in the northern Europe, we have a trend towards wetter condition, and in the southern Europe, you have a trend towards drier condition. That is also expected from climate modeling. Then in the last couple of years, the trend was the opposite, because for instance, last year we have a drought condition in 2018, we have a very strong drought condition in Germany, and also last year. But now, for instance, we can use this data, and as I told you, we have satellite SonMaster data available as an operational product from Copernicus, and you can easily download the data. It's really a matter of minutes, and you can compute SonMaster anomalies. And this animation shows the SonMaster anomalies from the beginning of January to 10 of June, because I did this map a couple of days ago. And brown color means dry condition. And for instance, if you want to see the current condition for the first 10 days of June, this is the map. and it is saying us that we are in Italy, we are recovering, because since from January to March to April, we don't have we have a very small amount of rainfall, so we are going to be in the drought. But in the last 20 days, we have a lot of rainfall, also today. But for instance, you can see that in the eastern Romania or in Hungary or now in UK, drought condition is starting to be a problem. And the same can be done by using, for instance, a semi-terrain approach. So basically using the precipitation instead of sun moisture. Again, I computed easily the precipitation anomalies from our semi-terrain ASCA dataset. And the map shows for Italy from September 2019 to May 2020, the anomaly condition of precipitation. And basically, if the map are red, it says that it's dry condition. If it is blue, it's the opposite. And you can easily see that satellite data are able to really see the low amount of rainfall that we have in the first 3-4 months of the year. Until 20th of May, we are also again in a very dry condition, but then we have rainfall. We were lucky because we have rainfall in the last 20 days. And that's the last slide of my presentation. I hope it was clear enough, but the key message is that sun moisture is a key variable in the water and energy cycle, and it is very important to be monitored from something. And we can now using not only in situ data, but also satellite data, because they have basically reached an accuracy and reliability level to be used for operational application. And as I told you, there are some products from satellites that are available in an operational context. And so there is a high potential to the operational exploitation of this data if you work, for instance, in some institution for for doing flood, landslide, or drought alert, and you can use this data for your application. You can find on the right some details on to reach me, but with my mail and the mail of our group, of our website, and I'm here if you have any question. Thank you very much for your attention.
Thank you very much, Dr. Brocca, for this really nice presentation. So now we will open time for questions. We actually received so far like 16 questions. So the idea is that I give you, that I read you the questions in a group of 3, and you can answer them. So here goes the first 3. Paul Munoz is asking which remote sensing product has the highest resolutions, or which one is recommended for South America? Also, in terms of real-time modeling, what do you suggest? Then from Agua Sustentable, they're asking, what about ERA 5 data? Is it useful? And then finally, Ronald Ontiveros, in your opinion, what are the new approaches and future challenges in soil moisture measurements using free data from remote sensors for application on a local scale? That's it.
Okay, let's try to answer. For currently, operationally, and so you can download the data from, but if you live in South America, it's different if you live in Europe. But currently, if you live in Europe, we have Sentinel-1 data that are available every couple of days with the spatial resolution that, for instance, a product is available with a 500 meter spatial sampling. This product will be available probably by the end of this year or early next year on a global scale, but the temporal resolution will be 6 to 12 days, because the coverage of Sentinel is more focused on in Europe. But if I have to, it depends on the application in which you want to make your you need the satellite sun moisture data. But the two products, there are 3 products that has a spatial resolution of 20 kilometers. So you say, okay, it's not enough. But my suggestion, and I wanted to show you in the presentation, was that you can use this data for your application, and you have SMAP data from NASA, SMOS data from ESA, and ASCAT thermistor data from EUMETSAT, so 3 different products. And my suggestion is try to test all of them. If I have to say one of them, it's not my way of, because I actually don't know which one can be the best one, and I don't want to promote one if it is not true. But these 3 products are available, and they can be used in South America. In South America, for instance, we found that with our precipitation estimates, we found very good results. For instance, in the semi-arid part of Brazil. And so it means that the satellite thermistor data and also precipitation data from satellite thermistor are quite accurate. Then what about ERA5? ERA5 is very good. It's very good mostly in the northern part of the world. So if you want in Europe or in US, it's really a very good data set. The very good things is that actually it is available with the good spatial resolution, 30 kilometers. But hourly time scale, and we do a lot of testing with satellite with precipitation from ERA5, and if you look at the north of the world, it is the best product on a global scale. If you want to use the product in Africa, and particularly in the Sahel, it is the part in which ERA5 has some problem, and so that's why I'm promoting our data set in that region, because it seems that we are better than ERA5. And also in Southern America, it's half and half. I can say that if you want rainfall data for northern part of the globe, US, Europe, ERA5 is a very good data set. If you want to use the data for Africa or South America and also Australia, satellite data set can be probably also a better option. And finally, what are the new approach? The new approach, I told you from the presentation that, for instance, we have a planned mission. Planned means that there are 3 planned missions from ESA called the Earth Explorer 10. One of them is called Hydroterra, and it is this new geostationary microwave satellite. If it will be launched, it will be really, in terms of our application related to thermistor precipitation, it will be really a game changer. But currently, another kind of sensor that I was not talking you in my slides is based on GNSS, which is actually I don't remember exactly the acronym, but basically it's a new it's a new techniques from satellites that basically use the GPS signal reflected from ground data to the satellite and to these new sensors. And with this new sensor, there are also companies working towards the use of such satellite for getting thermistor at, for instance, a 3 kilometer resolution, and depending on the orbit, because it can be put also on very small satellites, and depending on the orbit, temporal resolution can be very high. And finally, we have planned L-band SAR mission. And the hope is that this new mission will have a temporal resolution not every 30 days. That is very difficult to use for instance, in hydrology, in which temporal dynamic is very important. But if they will be available with a better temporal resolution, it will be an important source of data. I guess I replied to the first 3.
Yes. Then the next group of questions. Luca Picciullo is asking, what is the depth we are talking about? What is the depth considered for the comparisons? Then Vijay Duraisamy is asking, what are the obstacles for making Sentinel-1 data for operational soil moisture product? What is the best model for estimating soil moisture from Sentinel-1? And then finally, someone without name, he just put Lenovo. He's watching the presentation from a Lenovo computer. He's asking which model you have used in this slide. I don't know which slide is he referring for simulation and flood prediction?
The depth we are talking about from satellite is a few centimeters, and this is one of the obstacles in using this data for application. But for instance, in many of the applications in which you use satellite data, we applied some filtering approach called exponential filter or soil water index that can be used to estimate the root zones almost from surface almost to data. And it's quite simple, but it works quite fine, quite nicely. And so by using this filter, you can get an estimate of almost for a proxy, an indicator of almost for 10 to 20 centimeters that is quite useful for flood and landslide application. In the model that I've shown you in the slide is called, the name of the model is really unpronounceable because it's SCIRM, but you can find in the slide, but I understood that the recording on the presentation will be available, but also if you contact me, I can provide you the slides or you can find it somewhere. Also, you probably can find it already in my web page. And in the slide, you can see the link to the paper in which we have described the model in details. And the last question was, the second question, what are the obstacles for making Sentinel-1 data for operation? Actually, Sentinel-1 SONMOS2 is now currently available as an operational product from Copernicus. If you go on the Copernicus Land Monitoring Service website, you can find SONMOS2 from Sentinel-1 over Europe. Then they are working towards making the products available on a global scale. And the main obstacle of Sentinel-1 is technological obstacle because it's related to the data volume. The data volume of Sentinel-1 for 1 year is the same data volume of the previous MVSAT mission from ESA for, let's say, 15 years. So basically there is a problem, there is a technological problem. It seems strange that currently in which we have a cloud platform and very high technology, but processing the data and making them available in an operational context for this kind of huge amount of data is not easy. That was the main obstacle. But currently we have these products. Then if you ask me what is the best model for estimates of SONMOS2 from Sentinel-1, I'm not an expert in the retrieval of SONMOS2 from microwave, but there are two products, one based on the algorithm developed by University of Vienna and another one developed by people at CESBio in France. And these two products are available in their website. The Vienna product is available on the Copernicus. The CESBio product is available in the TEIA website. Probably in the slide there should be the link. And these products are available, have been available in the last, let's say, few months. And so we are now testing them. And for instance, we have now a project in which we are collaborating with these two groups for using the data for irrigation application. Currently, I don't have there is only one paper making a comparison, but it's not enough to say something about which one is more reliable. I have done.
Yes, thank you, Luca. We'll go to the next round of questions. Carlos Millán is asking about the SM2 Rain product, if it's a real-time daily product. I think he's probably asking about the lag time between the observation and the once it's is available in the website.
Yeah.
Then also someone from Lenovo Computer is asking, what is your observation on using cloud observation satellites for rainfall prediction like TRIM does, and in soil moisture-based rainfall products like SM2 Rain? Which one do you find more relevant with in situ data? And then Ankita is asking, how does SM2 Rain behave in case of continuous rain for a few days? as soil moisture might get saturated.
Okay, and SM rain is precipitation from, it's rainfall, not precipitation. It's rainfall from space, so it's a daily rainfall product obtained from soil moisture. So basically we get soil moisture from satellites, we apply our estimated rain algorithm, and we get rainfall data. Actually, estimated rain is the name of the algorithm because we can apply estimated rain to different satellite soil moisture data, and so we get different satellite rainfall products as an output, and this is actually what we are doing. But to make the answer simple is yes, it is a real-time daily rainfall product that has for the first release that is expected to be by the end of this year from UMETSAT HSAF project, it will have a latency of 12 hours. So for instance, now today at noon, you have the precipitation rainfall data for yesterday, for the whole day of yesterday. And currently it is expected to be available only for Europe and Africa and part of Brazil. The plan is to extend the dataset on a global scale. Technically, it's not a problem. But of course, it needs some time to make some testing, and we are a group of working on that. We are a group of 6 people, and so if we need time to make the processing. Then, what is the observation? The top-down and bottom-up approach. TRIM or GPM are top-down approach, and SM terrain is a bottom-up. We found in our papers that basically the two approaches are quite complementary, are very complementary. For instance, sometimes we get good results from SM terrain and bad results from TRIM, and the opposite. One complementarity is also that actually from SM terrain we get rainfall only over land. Once instead from TRIM or GPM we get rainfall also over the ocean. And indeed, we have now 3, let's say, SM terrain based products. 2 of them are based on the integration of SM terrain and GPM or a top-down algorithm. And so in that case, we are able to optimize or to get the best from the 2 approaches to obtain the best product. Then, actually you jump a question, but it's very long. But the question from Ankita, yeah, if it rains a lot, it can be a problem because of course, if soil moisture is saturated, we can't see rainfall anymore. But at 20 by 20 kilometer scale, it happens very rarely. It means that it is very difficult. Actually, in the paper of 2019 on EST, we basically do the computation on how frequent is that we get a saturated condition for a couple of days, and it's really happen on a global scale very rarely at 15 kilometer scale. Of course, once we are now moving at 1 kilometer scale, it might be a problem, and that's why we are going to investigate this in a more detailed way. But the only times in which we found that soil moisture is saturated for a few days is during hurricane. What is the name? What was the name? The hurricane that hit Florida and Texas a couple of years ago. In that case, soil moisture is saturated and we are not able to see precipitation anymore.
Okay, thank you. The next following 3 are the following. Daniel Verdugo is asking, what is the depth used in the analysis for drought monitoring? How important is this in reference with soil characteristic like in desert regions? Then Iliana Aldrete, she's asking about which remote sensing product would have the most reliable information in terms of best temporal and spatial resolution, and which one could you recommend for a country like Mexico that has such a large variety of climates? And then Adnan Buta is asking, what about soil moisture measurements by using GNSS reflected signals? I think you mentioned that earlier.
Yeah. And I'm trying to help myself with an image. No, this one. Recent. And for the, well, what is the depth used in the analysis of drought monitoring? It is, we get satellite data, we apply we get satellite data that is already applied the exponential filter. And so they should be representative of a depth of 10 centimeters. But we can also have an estimate of, with the same from Copernicus, again, an estimate of for 20 centimeters, but we are using 10 centimeters because it seems to be more related to our needs because actually we are running this kind of system in Italy to make seasonal prediction. Actually, we are running this this system for getting the current condition. And so we do from the integration of current condition with the seasonal prediction, we can give an estimate of the agricultural risk or the water resources risk in Italy. And this is what we are doing. And that's why we are using this depth. But of course, you can use a different depths. I have no experience in working in desert regions, but I can't say something meaningful because I don't have experience there. What I can say is that actually with the, for instance, Ascot and Mostu data is not good over the desert, so don't use such data. But other products can be reliable, but I never tried. GNSS reflected signal from for Mostu measurements. We started working with the people providing me with Mostu data from this new technique, and it's really nice because actually it's a different concept for measuring Mostu, because the Mostu from active signal is obtained from the backscatter, and in this case they use the forward scatter because it's basically the signal from the satellites or from the in situ station data to the sensor that is forwarded in. So it's very new. It's quite nice. We do some analysis, for instance, in Australia, but also on a global scale. The signal is much more noisy than SMAP, but the signal comes from the Cygnus constellation, that is a constellation of 8 small satellites. So the cost is really small. And in principle, you can launch a lot of them, like is doing Elon Musk. And so you can have spatial and temporal resolution much better. And we are in contact with a company called Spire that they have launched, they own indeed the GNSS system. And they are planning to launch more of them with also better accuracy. And so I expect that in the next couple of years, we will speak more and more about this new technology for measuring Mostu, and then of course to estimate rain for measuring rainfall. And finally, to answer to the guy who asked me information in Mexico, in the last paper in which that is this paper, I'm doing real-time slide just to give you an idea, but you can have more details in this paper. We have published this map that are 3-color map. You can see the map. Yes, no? My screen, yeah.
Yes, we can see the map, yeah.
And the map is the comparison of 3 products. GPCC basically is from in situ. The GPM is top down, and estimate rain ASCAT is the blue, is the bottom up. And when the map is blue, it means that estimate rain ASCAT is the best one. GPC, when it is yellow, GPCC, and when it is cyan, GPM. And if you can see in Mexico, the map is quite blue, even if not everywhere in Mexico. But you can use this map for getting an information about the accuracy of the three products. We are doing also similar map that you probably can find on Twitter, I guess, on our account, in which we do also the analysis by using the GPM plus estimate rain product that is this one, and not this one, but this one. And again, also this product is you can download. Now it's available from 2007 to 2018, and probably it's the most accurate product that we have. So if you want to make some testing, I could suggest you start from here, from GPM plus semi-terrain, test also semi-terrain ASCAT, and they could provide you good performance. Done.
Thank you, Luca. We have a little bit less than, well, like 5 minutes left. Hafed Ahmad is asking, any studies in MENA region to use these data sets? Also, someone from Galaxy M30 smartphone is asking coastal soil moisture estimation using Sentinel-1 and if it's comparable with rainfall. And then Vlad is asking, do you know any algorithms where using Sentinel-1 data actually improve temporal correlation of soil moisture with in situ data compared to ASCAT, SMOS, or SMAP products?
Okay, if the question is any study in the MENA region should be Arabia.
Middle East and North Africa.
Yeah, and yes, we have some studies on this region, and also we are doing a project there, but I'm not able to pick you to a particularly paper or study already done, finished in for that region. But if you send me an email, I can try to provide you more details because I need to collect the information. Then I didn't really understand which one are the other two questions that I'm trying also to read in the chat. One is related to the cost of soil moisture estimation using Sentinel-1 and if it is comparable with rainfall. If it is, as I told you, soil moisture from Sentinel-1 is available for the last 5-6 months. In the products even probably much before, but really it's really a small time in which we have this data. And we found that soil moisture improve ASCAT from Sentinel-1, improve ASCAT in terms of spatial representation of the soil moisture and then also of rainfall, but it adds noise because the soil moisture from Sentinel-1 is quite noisy. And it means that we need to make something better for improving this part of the product. But of course, we have just started. Once ASCAT SMOS SMAP are available for now for more than 10 years, 5 years. So there is a long-term analysis that have been done for these products. And for Sentinel-1, we just started now, and so much more should be done. Finished.
Okay, thank you. And then we'll go for the final 2 questions. The first one, Xiaoji, is there any disadvantage in the existing rainfall data set that motivates you to develop SM terrain? In another word, what's the advantage of SM terrain over traditional rainfall data sets? The second one is from Miguel Amuerde. What is your opinion on using the future release SWOT satellite for soil moisture detection? And finally, Mauricio Osorio is asking to develop landslides thresholds nationwide in Mexico. How big should the landslide record do you think should be? How many events and on what window of time?
Okay, actually looking at the, because some question is only private. Okay, you can see them. Because there are some question in the chat that you probably, Agustin, you are not able to see, but it's only to me. But I don't know if the chat will be available. I could try, but not sure that I will be able to make a reply to all the questions. But replying to the question that you did, why I was motivated to develop SM terrain, actually at the beginning, we build SM terrain not for estimating rainfall, but as an indirect approach for the validation of different satellite soil moisture data. The idea was we don't have in situ data of sun moisture like we have in situ engaged data. And so by inverting the signal, we can do the comparison with in situ rainfall and providing information about the accuracy of satellite sun moisture. Then the things changed because it's really basically out of our control. And so we started developing this satellite rainfall data set. As I told several times, we found it quite good for instance, mainly in a hydrological application in which we need accumulated rainfall estimation. And so I believe that for this kind of application with respect to other satellites can add value. And of course, you don't have in situ data everywhere in the world. And so, for instance, again, if you go in Africa or in South America, this kind of satellite product might be very, very useful. SWOT actually it's a mission not for sun moisture but for water level estimation from space, and the idea is to use SWOT for water level and river discharge estimation, not for sun moisture. Even though it is a SAR sensor, that so probably some application can be done, but I have no idea currently if there is some plan for that. And the last from Mauricio.
Question about the landslides, about the
landslide. How big should be the landslide record? I believe that landslide record means the number of landslides. Yeah, but of course, more is better. But we do the first analysis in Italy. Of course, we have more than 2,000. But we are doing now an application in India in which we have 130 landslides, and seems to be a good number. And the time windows is, I believe that more than 3-4 years is needed to avoid to have, for instance, very wet or very dry year that can be not representative for the long term. That's my reply.
Thank you, Luca. Thank you very much. We still have some questions left, but we're really running out of time. So I will share the remaining questions to Dr. Brocca, and maybe he can answer them later by email. Well, again, thank you very much for these really interesting presentations. Mauricio Osorio, who's the head of the group of hydrometeorology, will give like a final statement from your presentation. I will give now Mauricio the possibility to speak. So yeah, you can go, Mauricio. Go ahead.
Thank you, Agustin. Thank you, Professor Brocca, for this brilliant presentation. Today we got a very good summary of the importance of soil moisture for various phenomena related to hydrological processes like floods, droughts, and landslides. Also that it can be useful to estimate rain as an alternative to classic cloud observation, and even better in several regions of the world. Also a good summary of the different available tools to monitor this variable, I mean soil moisture, on various temporal and spatial scales. Again, we see another example of how useful remote sensing is on earth and environmental sciences. However, it is not a silver bullet. Remote sensing can be very useful everywhere, especially in countries with poor observation networks. However, in situ observations cannot be totally replaced with remote sensing. Remote sensing can be useful to complement observations, but we cannot be lured by the accessibility and affordability of it, and forget about the importance of in situ data. Well, that's my closure statement. Thank you everyone for attending our seminar. Be safe. Agustin, we're back with you.
Well, thank you everyone for joining this seminar. Next, I would like to show the future talk. If you can, yes, thank you, Luca. This week we have a very busy week. We have 3 other seminars. The next one we have is also from the same institution from Luca. We have Dr. Cristian Massari that will, on Wednesday at the same time, 10 a.m. Mexico's time, 5 p.m. Italy's time. He'll talk about the value of satellite observations for modeling and monitoring floods and droughts, and some open challenges. And then on Thursday, we'll have Dr. Angelica Tarpanelli, that she'll be talking about the stream flow estimates in rivers using multi-satellite observational data sets. And then on Friday, we'll have another seminar. This one is in Spanish from Jacqueline Fortin from Stanford. She will give a talk about using deep learning for improving fire forest prediction. So again, thank you very much for well, and then we have also on a couple of seminars on next week on green infrastructure and nature-based solutions. And well, for those that are still have not still downloaded the annual report from IMTA from our activities in 2019, you can download them at our website. Again, thank you for attending this presentation. Thank you very much, Dr. Brocca, and have a nice day, everyone. Bye-bye.
Thank you very much.
Thank you, Luca.
Ciao.
Bye.